Let's look at predator-prey models. Let R of t be the population of prey, like rabbits, and F of t be the population of predators, like foxes, at time t years. The population may be measured in hundreds or thousands or whatever. One system that models the interaction of these species is the Lotka-Volterra predator-prey model. dr dt equals 2r minus 1.2 rf, df dt equals negative f plus 0.9 rf. Now again, you don't have to have a 2 and a 1.2 and 0.9. The numbers could vary, but the predator-prey model is going to follow this format more or less. It's named after the Polish-American mathematician Alfred Lotka and the Italian mathematician Vito Volterra, who developed this theory independently and more or less simultaneously. Again, R is the population of prey, F is the population of predators. Let me explain to you why this system of equations makes sense. If there are no predators, in other words, if F is 0, then this goes away, and so we're left with dr dt equals 2r. We've seen that before. That's exponential growth for the rabbits, for the prey. Because if there are no predators, those prey will take off. Those rabbits are going to breed like rabbits, frankly. And this factor in front of the RF is going to be negative 1.2. We have negative 1.2 RF. Predator-prey interaction is bad for prey. So if you have lots of foxes, that means negative 1.2 RF is going to be substantial. And notice it's negative. It's going to take its toll on dr dt. It will decrease dr dt. Similarly, for df dt, if there are no prey, in other words, if r is 0, then this goes away. And so we're left with df dt equals negative f. Well, that's also exponential, but it's exponential decay. The predators die off exponentially, and we have a naturally declining population. Because if there are no rabbits, the foxes just die. However, the factor in front of the RF is positive, plus 0.9 RF. Predator-prey interaction is good for predators. So when you have lots of rabbits and lots of foxes, oh, this is going to be big, so it's going to increase the number of foxes. Let's graph R of t and F of t. If R is 0 equals 1 and F of 0 equals 0.5. We're going to let R be the x coordinate, F be the y coordinate, and we need to change this to x's and y's because the online plotters, they don't accept R and F. They want x and y. Now we could plot a direction field by hand. Remember we talked about direction fields when we dealt with Euler's method a few chapters ago. You would just plot dy dx for different values of y and x. So dy dx is dy dt over dx dt. Plug in different values of y and x into here, and then you calculate dy dx, and you plot a little line segment at that point with that slope. Yes, you could do that by hand, but why bother? It would take forever. We call the resulting graph a phase portrait, especially if we graph solutions. What's faster is graphing solutions using a phase portrait plotter. Just enter phase portrait plotter into a search engine like Google, and you'll end up with something. I like this one out of Bluffton University, but there are lots of them online. Okay, this is what you get. It's a phase portrait plotter. Enter these differential equations, 2x minus 1.2xy. You really should write it as 2 times x minus 1.2 times x times y. You probably don't need the star between the 2 and the x, but you really do need it between the x and the y. And similarly, dy dt equals negative y plus 0.9 times x times y. And we end up with something like this. So this is what we get. We get different solutions depending on the starting values. So we want to specify these as our solutions, or these are as our starting values. R equals 1 and F equals 0.5. And again, that doesn't mean we start with 1 rabbit and half a fox. I mean, these are measured in hundreds or thousands or whatever. Clear all curves, click submit, and this is what we end up with. It may seem kind of strange that we have this cyclical pattern, but actually it makes sense. So again, the x-coordinate is rabbits, and the y-coordinate is foxes. Or more generally, the x-coordinate is prey, and the y-coordinate is predators. Notice what happens as the x-coordinate, the prey, increases. The number of predators increase because they're feasting on the prey. But as the number of predators increase, as the y-coordinate increases, the number of prey, well, that decreases. They die off. until quite a few of them die off, and then the number of predators decreases substantially. And then when the number of predators decreases substantially, the number of prey increase, which leads to an increase in the number of predators, which leads to a decrease in the number of prey, etc. And you just get this endless cycle. If you were to graph them separately using time plots, you could just click on time plot over here. This is what you'd end up with. So notice, first the prey peak, and then predators. Prey peak, and then the predators, etc. Use the Runge-Kutta method, RK4 with h equals 0.1 to estimate the prey and predator populations for 0 less than or equal to t less than or equal to 2. We dealt with this when we had one differential equation. Now we have a system of differential equations. And there's a way that you can use Runge-Kutta to analyze that, but I'm not going to get into the hairy details. Just use some online software. Like the one out of Bluffton. Okay, you make sure you're using RK4. Click on this button, make sure it's RK4 and that h equals 0.1. And then click on table. And you get this. This would take hours to do by hand, but the table can be generated like that using online software. So basically what it's telling you is what the x-coordinate and the y-coordinate are for different values of t. So here we have t, this column is x, and this column is y. What would happen if we started at this point? Well, we know what happens if we start here. We're going to go around like that. And if we start here, we're going to go around like that. If we start here, we'll go around like that. If we start at this point, smack dab in the middle, we would just stay there. We wouldn't move at all. We'd be forever fixed, for all eternity. This is an example of what we call a critical point. A critical point is a point where dr dt and df dt are both 0. For example, let's find the set of critical points for the system we've been dealing with. Okay, so we'll set dr dt equal to 0, df dt equal to 0. Let's factor this. We factor out the r, and we get 2 minus 1.2f times r equals 0. From df dt, let's factor out the f. We get negative 1 plus 0.9r, all times f equals 0. So notice, if all of this equals 0, then either this equals 0 or this equals 0. In the same way, if all of this equals 0, then either this equals 0 or this equals 0. So we have two options here, two options here. That means overall we have 2 times 2, or 4 different options, 4 cases. So the first case is 2 minus 1.2f equals 0. So this first factor is 0. And this first factor is 0. So negative 1 plus 0.9r equals 0. Okay, 2 minus 1.2f equals 0. That means 2 equals 1.2f. F is 2 divided by 1.2, which is 5/3, or about 1.67. If we work with the second equation, negative 1 plus 0.9r equals 0, 0.9r equals 1, r equals 1 divided by 0.9, which is 10/9, or 1.11. So this is a solution. It's just a constant solution, equilibrium solution. R equals 1.11, F equals 1.67. This is a non-zero population of rabbits and foxes that can coexist. And that's actually the one that's smack dab in the middle here. So you start off with 1.67 rabbits, well, 1.6700 or 1,000 or whatever, and then 1.1100 or 1,000 foxes, and you stay there. Okay, let's try case 2. For case 2, this equals 0, 2 minus 1.2f, and this equals 0. So case 1, we had this is 0 and this is 0. Now we're choosing this equals 0 and this equals 0. So we've seen before, 2 minus 1.2f equals 0 leads to f equals 1.67. And then we also have f equals 0. Yeah, that's not possible. F cannot be 1.67 and 0 simultaneously, so there's no solution here for case 2. Case 3, okay, so we've already dealt with these two cases where this is 0. How about case 3 where this is 0, where r is 0, and negative 1 plus 0.9r equals 0. Okay, we've seen before that this leads to r equals 1.11. Yeah, that's not going to work. You can't have r equals 0 and r equals 1.11. So again, no solution. Lastly, case 4. R equals 0 and f equals 0. That's a solution. R equals 0, f equals 0. So you start off with no rabbits, no foxes. It's going to stay that way because they can't spontaneously generate if you don't have any. Critical points are what we call equilibrium solutions. In other words, they are solutions of the form r equals some constant and f equals some constant. So one equilibrium solution we saw was r equals 10/9, 5/3, about 1.11 and 1.67. That's the point that's in the middle right over here. So that's the point we talked about earlier. Another equilibrium solution would be 0, 0. So those are your two equilibrium solutions. Now we classify critical points based on what happens around the critical point, not at what happens at the critical point. We know nothing's happening at the critical point, it's just staying there. So the ones we've been looking at, like these over here, those critical points are called centers. A center is a critical point surrounded by simple closed trajectories, like circles or ellipses or ovals. A spiral point looks like this. So we have the trajectory spirals in. So maybe it's spiraling in, that would be a spiral sink, or it spirals out. In this case, you can look at the arrows and see that it's spiraling out. In that case, it would be a spiral source. So if you're going in, we call it a sink. It's like you can think of as stuff going down the drain. And if it's spiraling out, in other words, if you've got something like this happening, it's a source. Saddle point is a pair of trajectories approaching the critical point, and all others are unbounded as t approaches infinity. So here are the trajectories that are approaching the critical point. When along this line over here that's approaching the critical point, same thing with this one. So those are the trajectories that are approaching the critical point. Everything else is unbounded as t approaches infinity, because if you're not right on that line, then you go zoop, zoop, and it is really going to make that noise if you listen to it carefully enough. Zoop, zoop. Those just go off to infinity. They're unbounded as t approaches infinity. That's what's called a saddle point. The other kind of critical point is a node. This is a little tricky. Every trajectory approaches or every trajectory goes away from the critical point as t approaches infinity. So if you look at the arrows, in this case, this critical point, this node is a sink. So everything is approaching the critical point. Okay, like this. So they're all approaching. They're not going away from. If they went away from it, then the critical point would be called a source. This is a sink. And notice that at the critical point, every tangent or every trajectory is tangent to a straight line through the critical point. So all of these trajectories are tangent to this line, that line going through the critical point. So for instance, this one zips around, is tangent. This one zips around, is also tangent to that line. How realistic is this model involving foxes and hares? Turns out it's pretty realistic. So here's what the real life scenario is like. So this is not foxes and hares, but this is the trade of snowshoe hare pelts, that's the prey, and lynx pelts, that's the predator, by the Hudson's Bay Company in Canada in the 1800s and 1900s. So again, we can't really count the number of the number of lynx and the number of rabbits, but what we can count is the number of pelts that are collected. So the lynx is of course in black, lepus, it's Latin for rabbit. So notice that we have a rabbit population grow, and then the lynx population peaks right after that. Okay, not exactly here. Here it's kind of like that. Here it's like that. Here it's like that. So again, the rabbit population peaks, and then just a little bit afterwards, the fox population or lynx population peaks. Rabbit population peaks, a little bit afterwards, the lynx population peaks. Sometimes it doesn't quite work out that way, so we don't want to be fake. I'm not going to lie to you and say that it's perfect, but there is a connection. So it is interesting to see that this really happens. A system with logistic growth is of this form. This is where dx dt equals a1x plus b1x squared plus c1xy. dy dt equals a2y minus b2y squared plus c2xy. This is where the a's and the b's are greater than 0. Here's why. Because without this over here, you just have exponential growth, which is fine, at least initially. That's realistic. But after a while, that's unrealistic. And that's why we introduce this factor. Because when x gets big, this kicks in, and eventually the growth levels off. So logistic growth looks like this. It starts off rapid, like exponential growth, but then it eventually levels off. And that's what this is going to look like. So again, if you were to graph x, that's what it would look like based on dx dt. In the same fashion, dy dt would look like this. Okay. Now, as for the C's, C1 and C2, those could be positive or negative, and that affects the kind of relationship these animals have with each other. Not every interaction between animals is a predator-prey situation. Okay, this is telling me do not disturb is off, but just ignore that. Don't worry about that. Okay, so again, A and B are both positive. When the C's are less than 0, then we have competition. So that's an example would be lions and cheetahs competing for antelope. They both eat antelope, they both eat gazelles. They're competing against each other. So when you have lots of these, lots of lions and lots of cheetahs, since the number in front of this is negative, it's going to have a negative impact on the growth of the lions and the growth of the cheetahs. Both of these could be positive. You have cooperation between species. An example would be a remora fish eating parasites off of sharks. So again, here's a shark, and then there's this fish down here that's eating parasites off the shark. It benefits the shark because it gets rid of parasites. It benefits the fish because the fish gets to chow down on some yummy parasites. Gotta love that. So in this case, the C's would be positive because when we have plenty of X and plenty of Y, when those are large, it has a positive effect on the dx dt and on the dy dt. Both these are positive. So having plenty of remora fish, having plenty of sharks, that benefits both populations. And it's also possible that C1 and C2 have different signs. That would be an example of predation. That's the one we saw here. So here we have a negative sign in front of the RDT, or the RF factor, and here we have a positive sign in front of the RF factor. This means when it's positive, that means it's the prey. That means it's the predator. It profits from the interaction. Whereas if there's a negative sign, that means it's the prey. It does not benefit from the interaction. Speaking of cheetahs and leopards and jaguars and other animals, I thought this was cool. Difference between cheetahs, leopards, and jaguars. Cheetahs have solid individual spots, evenly distributed spots. Notice that leopards have this hollow spot in the middle. Leopards' rosettes are in large numbers with a slightly different color on the inside, whereas jaguars' rosettes are similar to leopards, but they're large and they have spots in the center. So how are we going to remember this? Well, cheetahs, these are like cheese puffs or, cheese balls. So there's no, they're not hollow. And jaguars, think of a J, a lowercase j has a dot on it. And in the same way, jaguar pelts have dots in the middle.